because today we're unpacking literally the greatest paradigm shift in human thought. We're talking about a mystery that baffled the absolute smartest minds on the planet for centuries and completely changed how we understand the very fabric of reality. We're going to ask a deceptively simple question. Is gravity really a force? Well, to figure that out, we have to go way back to where it all started.
So, set the scene in your mind. It's the year 1666 in England. A 23-year-old Isaac Newton is hanging out in the garden of Woolsthorpe Manor. He's actually hiding out there, escaping Cambridge University to dodge the plague. And while he's there, he watches an apple fall from a tree. Now, to you and me, that's just a completely mundane, everyday thing, right? But Newton has this brilliant, game-changing realization. He wonders, what if the exact same invisible pull that brings that apple crashing to the dirt is the very same pull keeping the moon glued to its orbit around the Earth?
And just like that single thought birthed Newton's law of universal gravitation. Honestly, his math was phenomenal. For over 200 years, 228 years to be exact, it flawlessly predicted planetary motions, it predicted the return of comets. I mean, it literally built the entire foundation of classical physics. But there was a massive, glaring mystery lurking right inside his equations. See, if gravity acts between the Earth and the Moon, across hundreds of thousands of kilometers of pure empty space, what actually carries that force? Like, how does the Earth reach out and yank on something it isn't even touching? Well, Newton himself was pretty honest about it. He famously said, "I frame no hypotheses." Basically, he could write out the math perfectly, but he had absolutely no clue how this spooky action at a distance actually worked.
Section 1. Einstein's radical question.
It took over 2 centuries for anyone to crack Newton's mystery. Enter Albert Einstein in 1907. He completely flipped the script. To wrap our heads around his massive leap in logic, let's walk through his famous elevator thought experiment. Okay, imagine you're in a completely sealed elevator, just floating out in deep, empty space. You are completely weightless. Now imagine someone straps a rocket to the top of that elevator box and accelerates it upwards at exactly 9.8 meters per second squared. Instantly, you'd feel pressed flat against the floor, right? You'd feel your normal everyday weight. But what happens if we take that exact same sealed elevator and just drop it perfectly stationary on the surface of the Earth? You'd feel the exact same weight. Inside that sealed room, there is literally no physical experiment you could run to tell whether you're accelerating through deep space or just standing still on Earth. And that right there is what Einstein called his happiest thought. We know it today as the equivalence principle. Einstein realized that a person in free fall doesn't actually feel their own weight. Think about an astronaut floating around the space station. They aren't actually being pulled by some magical tether. Free fall and weightlessness are the exact same state. So his genius leap was this. If you don't feel a pulling force when you're supposedly giving in to gravity, maybe, just maybe, that pulling force doesn't even exist.
Moving on to Section 2, the fabric of space-time. Space and time as one.
So, if gravity isn't an invisible rope yanking planets through an empty void, what on Earth is keeping the moon in orbit? Look at how the paradigm completely shifts here. Think about how Newton imagined gravity, an invisible force acting instantly across space, actively pulling the Earth to the sun. But Einstein saw it totally differently. Mass, like our giant sun, actually creates a heavy, physical depression in the very fabric of space-time itself. It's kind of like a bowling ball resting on a trampoline. The planets aren't being violently yanked around, they're just naturally rolling along that curved geometry. They are simply following the straightest possible path, which physicists call it geodesic, through a universe that is fundamentally curved.
So the absolutely crucial takeaway here is this. We upgraded from a classical universe where mass magically reaches out and violently pulls things instantly across a void, to a relativistic universe where mass passively curves the space around it, and that curved geometry is what guides objects. Gravity isn't a force of attraction anymore. It's just the natural, inevitable consequence of moving through a curved universe.
The brilliant physicist John Wheeler actually distilled all of Einstein's mind-bending, incredibly complex field equations into this one legendary quote. He said, "Mass tells space-time how to curve. Space-time tells mass how to move." Honestly, it's the ultimate, most elegant summary of general relativity. Mass and space-time are a package deal. They're completely inseparable.
All right, Section 3, the illusion of weight. Let's talk about why we actually feel gravity. Okay, I know exactly what you might be wondering right now. If gravity isn't a force, why do you feel so heavy sitting in your chair? Why does a scale show a number when you step on it every morning? Well, get ready because this is wild. Gravity is actually just trying to let you fall freely toward the center of the Earth's curved spacetime. That is your natural, effortless path, but the rigid ground beneath you is rudely getting in the way. The ground is constantly physically pushing up against your feet, stopping you from taking that natural fall. So this upward contact force, literally the floor smashing up against your shoes, is the actual sensation that your brain interprets as weight. You aren't feeling gravity pulling you down, you are literally feeling the Earth pushing you up. How crazy is that?
Which brings us to Section 4, the quantum frontier, and some major unsolved mysteries.
Now, let's pivot to the modern day, because the thing is, Newton wasn't totally wrong. When you actually break it down, his math is an unbelievably good low-energy approximation. We still use it every single day. We use it to build suspension bridges. And yeah, we even use Newton's math to launch rovers to Mars. It works beautifully for everyday life. But Einstein's general relativity? That becomes absolutely mandatory the second we start dealing with extreme gravity. Stuff like black holes, neutron stars, or even when we just need pinpoint accuracy for the GPS satellites orbiting our planet. In fact, without Einstein's specific math corrections, the GPS on your phone would drift off by about 11 kilometers a single day. You'd literally never find your destination.
And you can see the undeniable triumph of Einstein's theory mapped out perfectly right here. I mean, it started off incredibly strong by immediately solving this weird, unexplained wobble in Mercury's orbit back in 1915. Then he became a global superstar in 1919 when a solar eclipse proved that massive objects literally bend the path of starlight. And this entire timeline culminates in a truly monumental discovery in 2015 when the LIGO Observatory actually caught the physical stretching and squeezing of spacetime caused by two black holes colliding over 1 billion light-years away. Einstein predicted gravitational waves, and a full century later, we finally caught them on tape.
But here is where we hit a massive, glaring roadblock in modern physics. See, we have 4 fundamental forces in nature. 3 of them, electromagnetism, the strong nuclear force, and the weak nuclear force, they play super nicely together. They are beautifully described by quantum mechanics using subatomic particles. But gravity? Gravity stubbornly refuses to join the party. It remains locked in Einstein's smooth, geometric world of general relativity. And whenever scientists try to mash the math of these 2 incredibly successful theories together, the whole thing just breaks down into unsolvable, crazy infinities. Quantum mechanics and general relativity simply refuse to speak the same mathematical language.
Which leaves us, and all of modern physics, with the ultimate cliffhanger. If the other 3 forces are carried by little quantum particles, is gravity secretly carried by some yet-to-be-discovered, massless particle called a graviton? Honestly, nobody knows. It is literally the greatest unsolved detective case in science today. Is the future of physics going to reveal that gravity is purely just the geometric shape of the universe? Is it a quantum force carried by gravitons? Or is it something else entirely, something completely beyond our current imagination, just waiting for the next Einstein to come along and shatter human thought all over again?